Okay, so on today's show, circles. Circles in neutral geometry. We are not going to invoke the Euclidean parallel postulate, not yet. Circles the way you have come to remember them. So let's be very careful about what we mean when we talk about a circle. A circle is a locus of points, a fixed distance from a fixed point. So, oh no, this is some points, call it O. O is usually the center of the circle. There is some distance R, and so there's this point P that's on the circle. So let's say this is the circle with center O and radius R. That's the set of all points P such that the distance from O to P is R. It is exactly what you imagined from high school. That's what a circle is. So this segment is called the radius. If we were to draw a line segment from the circle to the circle through the center, that is called a diameter. We could talk about a chord. A chord is any segment with its endpoints on the circle. That's a chord. Technically speaking, the diameter is a chord because it has endpoints on the circle. We would say in this case that this endpoint and this endpoint are what we call antipodal, A-N-T-I-P-O-D-A-L, antipodal. We would talk about secant lines. A secant line is a line that intersects the circle twice. Whereas there are other kinds of lines that would intersect a circle only once, and those lines are called tangent lines. A tangent line ever so gently kisses the circle just one time. So that's all your vocabulary. That's the slide you're going to have to refer back to when I start throwing terms out there. You've got radius, diameter, chord, secant, tangent. All of them. Okay? Okay. So here's the thing. Here's one of the things we should talk about. If I have a circle and I have some line, and that line is going to let's split them up. If I have a circle and a line, and that line, let's group those guys together. I have a circle and a line, and that line is going to intersect the circle. Well, there could be no points of intersection. There could be one point of intersection, or there could be 2 points of intersection, but no matter how we go, there are only going to be 0 or 1 or 2 points of intersection. That's all there are going to be ever, ever, ever. 0 or 1 or 2. That's it. I will prove this when we gather in class. The way this proof goes says something like this. If I have a circle centered at O, and there are 3 points on the circle that are also on a line. So we imagine that there is some line like this. Remember, line's an undefined term. Maybe it looks like that. Who knows? 3 points cannot be on the circle and on the line. The proof is not too terribly difficult. It recognizes that these are radii, and once these are radii, that means something with respect to this angle and this angle. Deliberate pause. And once you see that deliberate thing, then you know, okay, I can't have 3 points of intersection between a circle and a line. Okay, but that's something that I will prove formally when we gather together. We should talk about special kinds of intersections. We should talk about tangents. If a tangent intersects a circle, really, I can't get a line that goes both ways, really? So if I have some line tangent to the circle, there is one point of intersection, P. Then it must be that the radius OP is perpendicular to line L. It must be. If the line is tangent to the circle, at that point of tangency is a right angle. And we do that by saying, okay, there has to be some kind of perpendicular, drop the perpendicular to the line, have it intersect at some point Q, and we prove that Q has to be P. And the way we do that is not entirely obvious. We say, hey, there has to be a point out here, R, where PQ is congruent to QR. If you connect the dots, we've got a congruent side, a right angle, and a reflexively congruent side. So triangle OPQ is congruent to triangle OQR by side angle side. Now that's ridiculous. OP is congruent to OR. And that means that if OP is congruent to OR, then the length of OR is the same as the length of this radius. And if OR is the length of a radius, then R doesn't fall on this line, R falls on this circle. And if R falls on the circle, then I don't have a tangent anymore. And that's a contradiction. So if I drop a perpendicular, it can't land anywhere but P. And so there's your proof. The thing that you will prove when we gather deals with secants. So I take some line, L, it's a secant line. It's a secant line. It intersects the curve at points P and Q. I claim that the center of the circle, O, has to lie on the perpendicular bisector of chord PQ. I argue that if I drop the perpendicular here, it is also a bisector. That's my argument. That's my claim. That will be the first thing that you prove when we gather in class tomorrow. Okay? These are neutral theorems. They work in neutral geometry. We'll talk about circumscribed. We'll talk about circumcircles and incircles in the next video. For now, it's enough to have a little bit of vocabulary and a little bit of interplay with circles and lines. So there. Very well.